Okay, so hello everyone. So we are coming to the second talk of today. So we heard a lot about Lean during this workshop. So our next speaker is the main architect of Lean, Leonardo de Moura. So he will talk about Lean, how AI and proof automation are changing mathematics. So please.
Thank you very much for the introduction. Very happy to be here. I want to tell you about Lean, and I want to start with this paper that has been published last year. Boris and Dustin solved open conjecture, right? So that has a $1,000 prize to it. It's really rare to have others open problem to have a $1,000 price associated with it. This is a lot for others problem. For me, the most exciting thing is that none of them knew how to use Lean, right? They even in the paper they say they vibe coded the proof, right? They were using ChatGPT and Lean. The paper assigns ChatGPT and Lean as co-authors. Actually, archive rejected. They had to remove, but on the author's webpage, you can find the official version, their official version, with ChatGPT and Lean as co-authors, right? But I think here the main insight is that we cannot trust AI. I mean, AI hallucinates, especially if you have a big proof. Nobody will spend time checking this proof. And here they got a machine checkable proof instead, right? ChatGPT not just helps them solve the problem, but also helps them formalizing Lean. And these were people that did not know Lean. Boris now knows, he starts learning Lean. He actually works for OpenAI now, but at the time of writing this paper, they did not know. What's Lean? Lean is a programming language and proof assistant, right? Everything is the same language, right? I mean, you can write code and you can verify code, you can write math, everything the same system. We have a small trusted kernel. The meaning here is that the kernel is how we call the part of the system that checks whether your proof is correct or not. Lean is a massive system, right? It has many bugs, but you only need to trust the kernel. In informal math becomes data that can be manipulated, changed, and here is the data can be exported. And you can check your proofs with independent checkers, right? We have several, and this is how we ensure the community that they can trust the results. You can check them with different checkers. And it's great that I'm talking after Patrick, because he made exactly the points I want to make next, is that Lean is very extensible, right? I mean, you saw in Lean verbose, Patrick did not have to coordinate with us. He could implement his own extensions without talking to us. And they're fully integrated in the system. You can even implement the extension in the same file where you're creating your results. You're trying to formalize some math results, you want to add some extension, you can do it in the same file. This is possible because Lean is implemented in Lean. You don't need to learn a new language. We believe in convenience. I mean, making sure that you can extend the system and write your math, verify programs, everything using the same language. We thought this was powerful. And that's what happens. I mean, the math community has Mathlib, this huge mathematical library, has more than 2 million lines of code. The last time I checked, more than 50,000 lines there are Lean extensions. They made Lean their own, like Patrick's making Lean his own by adding Lean verbose that enables him to teach math using formal mathematics in a much more convenient way. Several people tell me that they see Lean as a game. Kevin Buzzard once told me that he prefixed this claim by saying, I hope I'm not offending you, but you have written my favorite computer game. And when you use Lean, you have your file that you are editing. And here we have a small example where I'm defining that the natural number n is an odd number if there is a k such that n equals 2 times k plus 1. And you can write proof. You can write a theorem, right, stating that if n is an odd number, then the square is an odd number. And by a board game, you can click at the beginning of the proof. You're going to see the initial stage of the game, right? So on the right-hand side, you have the boards. You can see the game board. You can view it as the game board. We call it the info view. And the moves in this game are called tactics, right? For example, you can call intro. And here we're introducing the fact that n is an odd number. And we know there is a k. You can give a name to this k. You can call it k1. You can give name to hypothesis, right? I mean, in Lean, you can give name. We're calling it E1, the fact that n equals 2 times k1 plus 1. And you can see this is the new state of our game. You can call this simplifier. That's the most popular move by far. There are more than 100,000 calls to the simplifier in Mathlib. And here we're telling the simplifier to replace n with 2 times k1 plus 1 and expand the definition of odds number, right? And you have the new state of the game. This, you see that we're trying to prove an extension. You can provide the k using the exists move. We're giving what the witness is. And then we're calling linear integer arithmetic to finish the game. Each tactic transforms the goal until nothing remains. At the end, the kernel will check your proof. The kernel catches mistakes, right? Even the interface catches mistakes. Suppose that you're trying to prove that 3 is an odd number and we say the witness is 2, but when you try to prove the facts that 3 equals 2 times 2 plus 1, Lean is going to come back saying this is false. You don't need to trust me or my automation. You only need to trust the small kernel. And we have multiple independent kernels, right? You can even implement your own kernel. Many different people in the community have implemented their kernels. We want now to motivate more people to implement kernels and submit them to the arena.leanlang.org. Arena is a website where we keep a leaderboard. We're comparing kernels by correctness, if they are correct, and performance. Mathlib, we will run Mathlib on all. We are going to check Mathlib and other key projects every night. We also have negative examples that must be rejected. And people can submit both. They can submit kernels and corner cases that you want. For example, you may not trust a specific kernel and you want to check whether they're checking this corner case, and you can submit, and Arena will try all of them for you. This is particularly important because AI is getting really good at finding vulnerabilities, right? And we want to ensure the machine checkable proofs that are checked by machine are absolutely correct. Lean is also a development environment. I'm here, have a picture of Visual Studio Codes. That's the favorite editor used by the community. Well, some people like Vim too. I mean, we also have a great plugin. Patrick actually is one of the people that love the Vim plugin for Lean. I would say both VS Codes and Vim are the two favorites by far. And we have really strong plugins for them. And most users would use Lean in this way. They would split the screen where on the left-hand side, they have the file they are working on, and the right-hand side, you have the info view or the game board, where you show the state of your game. But now, many users are switching to a 3-panel mode where you have an AI on the bottom. And the AI, especially for new users, it helps onboard new users. It teaches you how to use Lean. You can answer questions in natural language. You can even interact with Lean in natural language. For example, in this example, I'm defining the summation function and trying to prove that 2 times sum of n equals n times n plus 1. I put a sorry here that's basically saying a placeholder saying I don't know how to prove that, or I don't want to prove it. I know how to do it, but I don't want to do it right now. And that's why we have a squiggly line saying, well, this theorem is using sorry. And I can ask the AI, prove the theorem for me. And we'll come back, not just with the proof, but also an explanation in natural language what it has done, right? We found this to be extremely powerful to onboard new users. We're seeing on social media all the time users saying, oh, I formalized my paper in Lean, using AI. And one point we like to make is that reading formal mathematics is much easier. It's much easier to learn to read than to write. But let's see. After the AI has formalized it, you can use Lean to inspect the result and understand exactly what happens. This is the proof that the AI came up with. You can see, you can click the by, you're going to see the initial state of the proof. You can see that AI is trying to do a proof by induction on n. You can click on the 0 case, it's going to tell you that you are trying to prove that 2 times sum of 0 equals 0 times 0 plus 1. And the AI finishes the proof by just saying simplify by unfolding sum. You're going to complete the proof. And you can see the inductive case, right? You can see the inductive hypothesis there. You can see the goal you're trying to prove. You can see the AI saying, oh, unfolds the definition of sum. You can see now how it affects the goal you're trying to prove. You can, the point I'm trying to make here is that you can visualize the proof. Even when the AI finds the proof automatically for you, you can use Lean to walk through. And you can start asking the AI, I don't understand this step. Or for example, you have here, he writes, what's num nets.mol.add? You can click and Lean will tell you, this is distributivity. This mol underscore add is just distributivity. Is the theorem that says that n times m plus k is n times m plus n times k, right? You can visualize everything. Mathlib, it's impossible to talk about Lean without mentioning Mathlib. Mathlib has more than 200,000 theorems, more than 750 contributors, right? It goes from basic algebra to modern research mathematics. Kevin Buzzard told us that he believes there are less than 1,000 missing definitions in Mathlib to be able to cover modern research mathematics. The Mathlib initiative, the Lean Flow, we want to support that. We want to make sure that you have all the basic and all definitions that are necessary to cover modern research mathematics. It's important, again, to view formal math. In formal math, math is data that can be manipulated. This dependency graph is automatically generated from a specific project that has been formalized in Lean. I believe this was the perfectoid spaces. This was not created by hand, it's automatically generated using the information provided by the formalization. It's our belief that Lean became popular with the math community after the liquid tensor experiments. This is a project that happened in 2020 when Peter Scholes posed a challenge to the community. He mentioned that in 2019 he was obsessed with a proof of a theorem that he claimed that was the most important result of his career. He was getting crazy over it, and he had doubts about the correctness. He couldn't keep everything in his head. At the time, I recall Kevin Buzzard telling me that they're going to try. It's probably going to take years, but they're going to try anyway. And to our surprise, after a few months, a team led by Johan Komelin managed to verify the key results that Scholes wasn't sure about, with only minor corrections. But the really impressive part came later. They not just verified, but they also simplified the result without fully understanding the result. This is before AI, right? This was just a proof assistance helping mathematicians going beyond their cognitive capabilities. Right? I love this quote from Peter when he said that the Lean proof assistant was really that an assistance in navigating through the thick jungle that the proof is. The result appears on Nature, and I think was an inflection point for the whole community. Right? But I think the main message here is that Lean is a navigation tool. Here, Lean was helping Jose to navigate through this proof that he almost went crazy over. The value here is not just correctness, it's understanding, right? You can click any definition, you can inspect the type, you can trace the dependencies, you can view the proof as a map, right, that you can navigate. It is not a static document. It's not something you print. It's something that you can interact with. Formal math is the first medium where mathematical knowledge is machine. You can navigate this knowledge, right, interactively. And since then, Lean's taking mathematics by storm. 6 different fields medalists engaged with Lean. We have projects like Equational Theories project by Terence Stahl has been completed. These are projects where Terry was trying to explore how large numbers of people can collaborate in a project. And here in this project, he had amateurs, computer scientists, mathematicians, high schoolers, many different people contribute to the project. But this was possible because you have a machine checking every single step. The Carlson's theorem is another big project that has been completed last year. There is the sphere packing that has been formalized. It started as a formalization project with students at CMU. I will talk more about that, but AI helped, assisted the project. I will talk more about this one. And now there's also formalized theorem, a massive formalization project led by Kevin Buzzard. If you want to learn more about formal mathematics and the impact, I strongly suggest you to watch this podcast with Terry at Lex Friedman. Lex Friedman is one of the most influential podcasters in the US, and it's a really good one, this one. I mean, and Terry spent more than 40 minutes talking about Lean, formal mathematics, and AI. And even one cool thing about formal math that you catch, although the goal here is not to catch mistakes, but to improve understanding. You do catch little mistakes. The first paper that Terry tried to formalize, his own paper, he did that to learn how to use Lean, and he found a tiny mistake, right? And when he was playing the game, right, he used a tactic, and the tactic came back, this is false, and came back with a counter example. Since then, he added a footnote to his paper saying that Lean caught the mistake, right? And another point he made that when he was at Lex Friedman is about refactoring. At that point, everything was being done without AI support. And he pointed out that it takes 10 times longer to write a formal proof, right? I mean, especially in his case, that was one of his first proofs he was trying, right? I think this comment is about the second project he had with Lean. But he pointed out one thing that he really liked is maintainability. He had a result where he had a constant 12. A new paper came out, and he said, oh, I can improve the result. I can replace 12 with 11. In the past, he would have to manually check step by step which parts of the proof have been affected by this modification, and now he can simply replace 12 with 11. Most of the proof still works. and he will get the squiggly lines. Lean will tell exactly which parts have to be updated. And this, for him, this was new, right? It's a tool that's not just helping you to find mistakes, but also to update and to maintain your results and propagate results coming from other papers. Formal math is a way to communicate better, right? Formal math produces precise and a result that you can navigate. You can navigate the logical structure. It's much easier to read than to write. It's easier to read formal mathematics than to read LaTeX. You can navigate. LaTeX is a static document, right? You cannot click a definition and jump to its definition. You cannot inspect the type. You cannot trace the dependencies with a click of a button. For example, here I have a picture of a file in Mathlib. You can click any place in the proof. You can see the state of the game. And this is not a static object. You can click any objects in the info view, and Lean will tell you the type. You can jump to the definition of the object. And now with AI, we have all this infrastructure for helping you to understand. And with AI, it can explain to you in natural language. It's extremely good at doing that. And it's just getting better and better. The next models, people that have seen previews of them, are already telling us that it's way better than what we have right now. It's not just verification, it's a way to communicate mathematics, right? At the frontier of human comprehension. It's about understanding beyond your cognitive abilities, right? Modern mathematics, like it shows this project, right? They create structures that exceed human working memory. This will happen. We have to keep in mind that the problems we are trying to solve, not just in mathematics, but also in software development, hardware development, they will go beyond our comprehension. Right? Everything. We're going to have trouble keeping all objects in our minds. You're going to have hundreds of interconnected definitions. No single person can hold it all. Right? For math plus interactive tools is a cognitive amplifier, right? The real bottlenecks in mathematics is not proof, it's comprehension, right? We want to help people to understand results, right? For mathematics is a way to handle that. A colleague of mine once said that he only uses a math results if he can prove himself the results. The problem that this doesn't scale. We are going to have one point that one lifetime will not be enough for you to reprove everything you need, right? I want to show you another example, and this is using a model that has no special training for Lean, right? It just saw Lean on this training data, right? They train on GitHub. They can see Mathlib there. Not just Mathlib, but the whole history of changes to Mathlib and Lean, right? And I just define as prime numbers locally. I'm preventing the model from not giving it access to Mathlib. I'm just saying define prime numbers and asking the model to prove there are infinite number of prime numbers without any access to Mathlib. Without all the infrastructure we have in Mathlib, just asking, prove these results. It came back later with a proof. I mean, every step has been verified by Lean. The AI explains the proof structure, and you can replay the proof without AI. I think that's one value. When the AI finds a proof in a proof assistant, it will produce the tactics, right? The game moves to solve this problem. You can use them to replay without using the AI. And it's also invented all auxiliary definitions, right? It defines factorial, right? We do not need have factorial in this file. We define factorial, prove basic facts about factorial, like it's always positive, all by itself. And the main theorem is the Euclid's proof strategy, right? You can see also he proved auxiliary theorem saying that if n is greater than or equal to 2, then there is a p that's a prime number and p divides n. It came out with that by itself. Of course, he has seen the proof that there are infinite prime numbers in textbooks. But from this knowledge it saw during training, he can reconstruct the proof in Lean. AI explains its reasoning, right? Explains it in natural language. It came up with 5 definitions, the theorems, with a clear mathematical motivation. The formal proof follows Euclid's classic strategy, right? Every step is verified by Lean. The natural language explanations help humans to follow, right? The formal proofs don't have to be opaque. AI bridges the gap between machine-checked rigor and human understanding, right? We have to keep in mind that the IDE is a way for you to interact with the objects, right? I wrote about that. I put a link on an essay, Proof Assistance in the Age of AI, showing that how critical it is to have a proof assistant that has all this capability of visualizing results, being extensible to, for example, Patrick Massot was demoing Lean variables. The AI will also learn to use Lean variables, right? It will be able to not just write proofs in Lean native language for statistics, but also learn to write it using Lean variables and address a concern that some people have that proofs are not readable. This all will happen. It's just a matter that up to this point, formal mathematics was not a priority for AI labs. It is becoming a priority now. And we are going to see dramatic improvements in this area. Oops, sorry. Okay, what we learned, I think the main important lesson we learned in this adventure is that it's not just about proving, but proof assistants are not just about proving, but understanding complex objects and proofs, getting new insights, navigating through structures that are beyond your cognitive capabilities. Machine checkable proofs enable a new level of collaboration. For example, for the liquid tensor experiments, it enabled people to collaborate that never met in person. It also enables us to collaborate AI that we do not trust, AI that will try to deceive us, right, in believing something is true. Another important lesson, in my point of view, is that auto-refactoring and generalization now is much cheaper, right? I love this message from Ricardo Brasca in this Lean Zulip. Lean Zulip is a communication channel where the community gathers. Here, he posts a message celebrating that they had a tool that generalizes a result, not just generalize the results, but propagated the generalization. And he highlights the points that imagine someone has generalized as a result on a 50-year-old paper. And now you have to propagate the results manually to all papers that depend on it. Nobody would do it, but with formal math, we can. This is feasible with formal mathematics. A question now that we get all the time is, do we still need proof automation in a system like Lean? Can AI do everything? Can AI even write? Maybe AI, you don't even need statistics. The game moves. AI can write the proofs in term mode you can view as the machine language for formal mathematics. Maybe I can write that directly, right? But our answer is that better statistics means better game moves and shorter proofs. Better statistics mean more powerful AI. I will tell you a little bit about a new move we have called grinds, and is a move that removes a lot of boilerplate from Mathlib. We like to see PRs like this one where a big chunk, all the red part has been replaced by a single line using grinds. And one of the maintainers is showing that he's really excited about this change. This basically, we see this kind of automation as a way to remove boilerplates. But what is grinds? Grinds is a new proof automation that we released last summer, has been developed by Kim Morrison and me. It's inspired by modern SMT solvers. SMT solver you can view is the kind of proof automation that operates by adding facts to a whiteboard. We call it a saturation tool. It keeps accumulating facts on a whiteboard. And what do we put there? We put new equalities, new inequalities. We have specialized solvers like for linear integer arithmetic, commutative rings, associative and commutative operators. And you keep accumulating these facts. And more importantly, is that grind supports full dependence type theory, right? SMT solvers, a class is a category of automated prover that operates on first order logic. But in Lean, we have dependence type theory that's more expressive, that's essential, was essential so far for the success of Mathlib. And it's really important for us that grind can understand dependence type theory. There is no translation layer. It operates directly at dependence type theory. It understands the type class mechanism in Lean that's used massively by Mathlib. It can understand advanced features like dependent pattern matching, and it's producing a Lean proof. We said that it has many solvers, right? But how does it work? I think I have here a small example to show how it works. For example, we have this theorem that's saying that if a plus b plus c equals 3, a squared, b squared, c squared equals 5, a cubed plus b cubed plus c cubed equals 7, then the ring solver will learn that a to the 4th, b to the 4th equals 9 minus c to the 4th. From there, the congruence closure will learn that f applied to these values, they are equal by congruence. And then linear arithmetic knows that 2 times something cannot be 1, right? And basically here in this example, we have 3 different solvers working together to solve a problem. Grind is one of the fastest growing tactics in the linear ecosystem. Since we released it last year, there are more than 5,000 occurrences in Mathlib. We're really happy when Terry starts using grind without us telling him that grind existed. And he was viewing grind as good old-fashioned AI, right? One thing he liked about grind is predictability, right? He reports success in seconds or failure in seconds. And when there's a failure, you get information, you get diagnostics information. And since then, grind has all these solvers. One thing that we strongly believe in Lean is that everything should be extensible. And one way to extend is to allow users to control the behavior of grinds and also allow the AI to control the behavior of grinds. Instead of grinds having a fixed strategy, a hard-coded strategy, we want to allow users to interact with grinds. Users to add their own new grind moves in the same way Patrick Massour adds new syntax, a complete new mode, Lean verbose to Lean. You can do the same in grinds. And we are betting that the AI will learn to play not just the Lean game, but also the grind sub-game. In this example here, you're trying to prove that cosine x plus sine x squared equals 2 times cosine x plus sine x times sine x plus 1. We have the game, the initial game, and we can tell grinds use this identity, right? The cosine square plus sine square equals 1. And after that, use the ring solver. This completes the proof. The main point here is that here we are removing from grind the responsibility to guess which theorems from the library are important. We are letting the user or the AI to control this guessing part. Better tactics implies better AI, right? Grind closes a goal, right? When it closes a goal, some of the proofs correspond to many mechanical steps that nobody wants to spend time applying them. For example, I here have an example from a paper in quantum algebra. The paper is called Categories Generated by Trivalence Vertex. Kim Morrison is one of the authors of this paper. And Kim was telling me this paper was a reason they got excited about formal math. At the time, this paper uses a computer algebra system that is not verified, and it felt wrong to have a paper with a result that was some of the intermediate values were computed by a computer algebra system that may have bugs. Here, Grind is using a technique called Grosvenor basis to finish this proof. There's thousands and thousands of steps behind this single call. It's a completely mechanical procedure. There is no point on a human performing these steps or the AI performing these steps. AI will try, you have to keep backtracking, trying many different things until it converges. It's a waste of energy, a waste of resources. And here you are saving resources by using a specialized procedure. Now, AI is getting AI for math is getting very popular. We have 3 different systems that manage to reach at least silver medal level in international mathematical Olympiads. All of them used Lean. No competing platform was used by any of them. One reason for them to use Lean is, I think there are multiple reasons. One, that Mathlib exists. Another one, that Lean is extensible. And because Lean is extensible, they can use Lean to extract information about Lean in the proofs created using Lean. When Alpha Proof got a silver medal in 2024, I think nobody was expecting that. 6 months before they announced the results, people were claiming that it's impossible for an AI to get any medal at the IMO. That solving IMO was a sign of true intelligence. It's funny that since then now I find in social media people saying, oh, this problem is easy. It's like IMO problem. It's easy for AI. But 2 years ago, people would claim that it's impossible for AI to do it, right? I think the lesson here is that it's not going to stop. We'll keep getting better and better for a while. We have not reached the ceiling yet. Now, since then, also there are multiple startups building AI for mathematics and for software and hardware verification. I listed 4 of them here. Their combined valuations more than $3 billion at this point. And they are not limited to math. They want to do software and hardware verification. They see the power of machine checkable proofs. For me, recently, these next results where the AI helped to formalize A result that Marina Wiazowska got a Fields Medal in 2022 was a big deal. The project was being led by students. Sid, I like him a lot. I met him last year. Was leading the project. They created the blueprints. They deserve all the credit for this effort. I know that this result was controversial because the AI company that formalized completed the formalization did not interact with them. But the fact that this is possible is interesting independently of all the conflicts that happens with the community. I don't view like AI replacing mathematicians. I see it as empowering them. I'm finding every week a new mathematician, a new amateur mathematician saying AI helped them to use Lean. This is a win for the community, for the math community, for the proof assistant community. And if people told me a few years ago that AI would be able to come up with 200,000 lines in just 2 weeks for a result of this magnitude, I would say no way, right? I mean, this is impressive. And AI, of course, this is not perfect. The proofs have to, AI has to improve on producing readable proofs. But this is going to happen. We have to keep in mind the AI labs so far, they were trying to prove they could do it. For example, when Alpha Proof was built, the goal is to prove that you can get a medal in the IMO, not that you can create a readable proof. But providing readable proof is in scope now. When I talk with them, they all say this is in their roadmap now. Why Link, right? Why all these startups and big tech companies use Lean? I think one is because Lean is implemented in Lean. You can use the Lean APIs to access all the internal data structure, right? You can control the environments using the Lean APIs. You can visualize everything. You can export the data, and this is very convenient. You can build tools like Pantograph that use the Lean API to control. You can write a small, your own little server that controls Lean, that allows the AI to control Lean. Second reason, Mathlib is training data. It's high quality training data. Mathlib provides a coherence visualization of mathematics. Right? You don't have 10 different definitions of ring. You have only one. Everything's uniform. The library always tries to give the most abstract version of the results. A friend of mine jokes that AI is so good at Lean because the main corpus of Lean today is Mathlib, and the quality is really high. And so AI has seen lots and lots of Lean code that's extremely high quality. The machine checkable proofs, of course, this provides a signal to reinforcement in a reinforcement learning loop. Lean is open source, no vendor lock-in. I talk about other aspects in this essay called Why Lean. One of them is, the last one is that all Lean developers listen to the community, right? I mean, embracing, for example, classical mathematics was one thing from the beginning we embraced it in the Lean community. And the Lean developer team embraced it from the beginning. The feedback loop with better automation, we create more compact proofs that allows us to train better AI, that brings more users, more libraries, and repeats, right? I don't believe AI will make formal methods obsolete, especially decision procedures. I mean, my area of expertise is actually decision procedures, automated reasoning. Many people in my community feel like, oh, we are useless. I don't feel that way. I feel like this area of decision procedures, there's a part that's very algorithmic, and this part is going to stay. You have efficient data structures, efficient algorithms for performing operations. And there is an algorithmic, there is this algorithmic part, but there is a heuristic part that's actually I never like it. It feels like black magic. You're trying to hard code heuristics. And actually, AI is much better at that. I mean, AI shines at this kind of coming up with heuristics. The neural network can capture your tricks for solving problems much better than you can capture them with codes. Right? Combine the two is powerful. AI also, another thing for me was unimaginable, right? I'm super old school. I never imagined AI would help me to write code, to develop Lean itself. I always thought, come on, these tools are crap. They are useless. And they were useless until last year. They were completely useless. But one day, Kim Morrison came to me and saying, look, let me show you this factoring step. More than 10,000 lines. It's a tiny change to Mathlib. 10,000 lines. The library has more than 2 million lines. We were making a change to Lean that had to adjust 10,000 lines of Mathlib. And this was done using AI. And Kim showed me, look, this is how we scale now. Because Kim was always pointing out to me, Mathlib is going to get 10 times bigger. How can we keep it in sync with Lean? We're going to have to keep adding more and more people. But now Kim was saying, now there's the answer. AI will let us scale. To this, there's no limits anymore. Another thing I realized is that how much, well, I always knew that developing real software is really painful. But I didn't realize how much modern AI can remove. It can remove lots of pain. And I actually believe one of my superpowers was that I can tolerate lots of pain. But this superpower is no longer relevant. AI now can help us isolate issues. Right? It's superhuman behavior in isolating issues in Lean. When a user now comes, oh, this behavior is counterintuitive, I think this is a bug, AI can help us isolate it. I don't know any Lean developer that is as good at isolating issues as the AI. It can try new ideas, even if the code is not high quality, it's not up to our standards. We can try the idea and see if it's worth investing our time. In proof of systems, automated reasoning, you try ideas, most of them do not work. They do not perform as we want. And having a way to try experiments quickly, it's super useful. It completely changes. I think every Lean developer has this sense that their life was miserable because you're always analyzing traces. The traces are massive. And now you have a new tool that can help us scale, that will enable us to maintain a mathematical library that's 10 times bigger, 100 times bigger as we keep pushing forward. In the validation, I want to emphasize the validation bottleneck. That's AI, without many people try to pitch that AI doesn't need formal mathematics. I think this is a huge mistake. People keep saying, oh, we're going to put many AIs working together, checking each other's results. But at the end, you have a result that some human experts will have to manually check. The results you cannot navigate. You have no infrastructure for navigating the result because it's written in natural language with LaTeX. Lean automates the validation step, not just that, but also visualizing the results, right? And another thing that people do not understand that we have to keep telling outsiders is that Lean only helps checking the proof, the statements. An expert has to be there. A statement that says, yes, this is capturing this formal statement, captures my intent, right? The formal statement is our trust anchor, right? I every week now I get an email from someone claiming they proved the Riemann hypothesis using Lean. 99, of course, all of them that have bugs in how they stated the results, and being able to visualize the results, the formal results, is important. And validation is more important than ever. AI they have this capability of finding vulnerabilities. Keyword hacking is one of them because they have been trained in reinforcement learning environments. If during the process they learn that they can exploit an unsoundness, they will do it, right? It's a way to accomplish the goal in a very efficient way. I wrote about that in this essay. Who watches the provers? We have tools like comparator that allow sandboxes using external checkers, more than one external checker, allowing you to provide a reference statements for some open conjecture. And we also have now a chapter in the reference manual talking about what does it mean to validate a formal proof. The Lean Flow. The Lean Flow is a non-profit. We have 20 engineers working full-time. Lean is open source. It's controlled by no single company. Sebastian Ulrich and I launched the Lean Flow in 2023. We like to say now that before 2023, Lean was a research project. I mean, and we would push back to the community saying, come on, folks, this is our research project. This is not a product. I mean, that you should not expect a product level quality. But this completely changes with the Lean Flow. We run the Lean Flow as a startup. We view now Lean as a product that we are serving the community. Since we launched the Flow, we had 28 releases, more than 8,000 pull requests. Every month we have a new release, packaged with features, performance improvements, bug fixes. We have been analyzing the performance of Mathlib, and one cool fact is that Mathlib keeps growing, but we are managing to keep the build times constant, and actually they're even decreasing. The library is getting bigger, and the build times, we are getting faster and faster. Our public roadmaps are public. I put a link to the public roadmaps and a link to the whole team. ACM gave Lean the awards last year, and in the citation they say Lean became the de facto choice for AI-based systems of mathematical reasoning. And what else we are building? We are building Lean, but that's not the only thing we are building at the Lean Flow. We are building many tools, satellite tools. One of them that I think will have a huge impact is Verso, right? Verso will enable us to write papers with Lean codes that is checked. You can mix LaTeX, natural language, Markdown, Lean, everything in the same file. I have a screenshot of Verso here showing on the left-hand side the Verso inputs, and on the right-hand side what is rendered, and is interactive. And actually, this slide deck that I'm using right now was built using Verso. Every single example is correct. There's no typo in any example. All examples have been checked with Lean. All the information you saw when I click on things on the slides was generated using Lean and Verso. Verso is implemented in Lean, right? All the results that you do with Verso are checked using Lean. You can use Verso to write lecture notes, papers, slides, everything in a single tool. The Lean website is written using Verso. My website is written using Verso. Verso is pure Lean, has been built by David Christiansen at the Lean Flow. And Lean blueprints, right? Lean blueprints, I mean, integrates the blueprints that Patrick Massot started, that was extremely popular with the community, and combines blueprints that's a great idea with Verso, everything in a single system. Many large projects use the blueprints, but the good news is that blueprints we can automatically translate. We actually did it. I mean, we translated the formalized theorem blueprints to the Verso blueprints, Carlson, sphere packing, and so on. We mapped all these projects to the Verso blueprints. I'm putting a link to the repo Verso blueprints. And the nice thing is that the blueprints are a way to map a result. You can visualize what is missing in your formalization, and you can have a central system where you're combining a Lean project, your informal natural language explaining the results, LaTeX, everything in a single system. And you can do that all in the same integrated development environment. It's also written in pure Lean by Emilio, also at the Lean Flow. This is one of the results that is available in blueprints. Both Jason Reed and David Renshaw are working on this formalization project. And you can see here you have Lean code that's interactive, mixed with LaTeX, everything a single interface that you can navigate, and you can jump to the Lean code at any point. This is the source for this example. You see in the same file, they're mixing LaTeX with Lean, and everything works. I mean, the hovering, all this information I told you about, you can visualize results, jump to the definition, everything works here, right? You can even visualize, that's another feature that's coming. You're going to be able to visualize in VS Code the rendering itself. And you can see the dependency graph, right? You can see the results. What the green ones is that they have been formalized and they're completed. You can see what's missing and so on, right? You can interact with this dependency graph. Another thing that's coming, the blueprint has been released this week. This is brand new, but something else that's coming soon is the Lean Workbench. The cool thing about Lean Workbench is zero installation, right? We don't want people spending time learning how to install Lean, the tooling, what VS Code is. Many people, they only want to work on their problem. They don't want to spend time learning on how to install Lean on GitHub and so on. The Workbench allows you to manage Lean and Verso blueprint projects in your browser. It's going to come pre-configured with AI. You don't have to configure yourself. It's great for teaching. If you're teaching a course, summer school, you don't want students spend 1 hour addressing technical problems the students may have. You just start your own server or use one of the servers we are going to provide, and the course is there. You can select which version of Mathlib you want. You can freeze a version of Mathlib. This is important, for example, if you're preparing a course, a semester. You want to freeze Mathlib. You don't want to be affected by changes in Mathlib while you are teaching the course. So you can ensure, as an instructor, you can ensure that the students are using the version of the library you want, right? And this is being built by Jason Reed at the Lean Flow. and Verso blueprints, they're all going to be integrated with the workbench. Well, I started the talk with this example for the Erdos Prize. But I want to finish saying it's not just about proving formal mathematics. Proof assistance is about understanding, communicating, and navigating structures beyond your cognitive abilities. Machine-checked proofs are both the trust anchor and the communication medium. Right? I love this quote that Terry said this in another podcaster that's also very influential, Dwarkesh Patel, a few weeks ago, saying that he sees in the future math projects where you have actually a high school student contributing, making real contributions to the project, because we have AI tools, Lean, and everything else, right? AI enables more people to use and benefit from formal mathematics. We don't need to take things on faith anymore. You have machine-checked proofs. I put here the links to the Lean websites, to live, the live websites where you can play Lean live on your web browser, a link to the Zulip channel where the community gathers, and a link to the reference manual with additional information about Lean. Thank you very much for your attention, folks. It was great to be here.
Hi, thank you very much, Leo, for this extremely insightful talk. So I will clap, maybe my colleagues will. Okay, so there are a lot of questions. We will take some. So the first one, is grind comparable to Isabel's sledgehammer?
Well, sledgehammer uses external provers, right? These provers are for first order logic or are variants of higher order, some support for higher order logic, like Vampire or Z3 that's I wrote. I mean, that's SMT solver. But I think a distinguishing feature here, these solvers are black boxes. If they fit, the first thing, they are for a logic that's much weaker. You need a translation layer. Another thing is that they provide awful diagnostics. I mean, when grind fails, it provides interactive diagnostics. Another difference is grind has this interactive mode. The other ones are black boxes. You cannot control them. The AI cannot control the other automated provers. While grind, you can steer as a user, and the AI can also steer, right?
Thank you. So there is a comment, more of a comment. So I would like a discussion between Patrick and Leo about the future of the planet. So I guess this is for the panel next. Now, the next question is, how do you see the quote, AI is bad at definitions, problem that was a recurring theme on the first day of the workshop?
Yeah, I think right now it's bad as definitions. I think people usually assume that the technology is going to stay stable. 6 months ago, AI was useless for my work. I would not use it for anything but search. I mean, I would use it as a better Google. Now it's an integral part of my workflow. And I don't think it's stopping. Everybody that tried the next generation models are telling me it's orders of magnitude better. This way, it is today bad definitions, but will not stay like that forever. I see it's a co-worker. I don't expect AI to produce final results, but to assist me to produce better results. I view it as a tool that's making me more productive.
Yes, thank you. So the next question is more quite philosophical somehow. It strikes me that there is an important difference between automatically generated natural language explanation of a formal proof and whatever a mathematician might have said to explain the proof. is there any effort to make sure the natural language explanation abides by any standards of naturalness or intuitiveness?
Yeah, great. Right now, what we observe is emergent behavior. Nobody, as far as when I talk to the big AI labs, none of them said this was a goal for them. What we see today is emergent behavior, and I find it really surprising on how good it is. The way it is, because it was not a goal. But this is a goal. When I talk to the same AI labs the last few weeks, this is a goal now. I mean, they see the power of the technology. They were really surprised that AI could write formal proofs for open conjectures. I mean, they want this technology to write more readable proofs. Will it ever be perfect? Probably not. But will it be useful? I'm fully confident that it will be useful.
Great, thank you. So the next question is, can you comment on the economics and business models? I guess it costs a lot to make a new cloud, for example. Who pays? Who makes a profit? Who oversees fair play?
Yeah, this is a great question. I mean, the first thing is disclaimer, I'm a scientist, not an economist, a business person. But I feel like we have seen this before. At the beginning of the computer age, we had people said we're going to have only 5 computers in the world, and very few people could had access to these computers. I think the same thing will happen with AI. 10 years from now, these models that are already very useful will be running in our phones. Imagine how the world was 10 years ago. I mean, I understand people concerned about the costs now, but it's not going to stay like that forever. I'm very optimistic about the future. I hope I'm not concerned about burning the planet, this kind of concern. I'm more concerned about the disruption in society, where what will happen if the AI keeps getting better and better and most jobs disappear, right? I think that's one. Uh, I feel like humanity will survive, but we will have a lot of disruption. This is a real challenge. I'm concerned about that, the disruption in society.
Thank you. So the next question, so you talked about formalization improving mathematical understanding, but the structure of lean code produced by humans is very different to that produced by generative AI. It's not just the proofs being unidiomatic. The bigger difference is in how definitions and lemmas are structured. Do you envision challenges in extracting mathematical understanding from large AI-generated lean developments, particularly if novel results are produced?
Yes, yes. That's why I think proof assistants are super important, right? We are going to interact with these results. Suppose that the AI comes, I solve the Riemann hypothesis. Suppose, I don't think this is in reach, but suppose it does in the future, a few years from now, and it comes with something that's incomprehensible. But you should not view it as a static entity. This is something that you can manipulate, you can transform, you can keep asking, you can interact with the AI, interact with Lean, and keep refactoring the codes, applying changes, restructuring. This is going to be an interactive process. That's why a proof of system is so important. It's a medium, it's an interface for us to manipulate these objects that are beyond our cognitive abilities. You can start breaking it in smaller pieces, refactoring. It's going to be interactive. We will build tools to help the process. I don't view this as a blocker. I mean, we should not view as what the AI produces is the final result, but something that we can interact with.
Thank you. So the next questions, for the validation bottleneck slide, do you see that a formal statement in Lean can also be used as a specification document in other domains besides mathematics, such as software engineering?
Oh, yes, yes. This is, I focus mainly on mathematics, but Lean is used for software verification. For example, Microsoft's cryptography is verified using Lean. Google has a project now using Lean for verifying Rust. At AWS, we have Cedar as a policy language that the model has been written in Lean, the spec has been written in Lean, properties about the spec has been proved using Lean. This is happening already, right? Some of these startups are working hardware verification, software verification. Yes, I mean, and their specifications are even more important. I mean, one thing I love about math that people have really good abstraction boundaries. The abstractions are beautiful. In software hardware, sometimes it's ugly, right? I mean, they're competing forces, right? Making something fast sometimes. One technique people use a lot is destroying the abstraction boundaries, right? And you have this ugly entity that you have to deal with, right? But yes, specs there are more important than ever, and we have to educate community, right? I mean, I see a bunch of people online saying, "Oh, you just going to press a button, the AI is going to come back saying, I prove, here's the verified version of the results." Well, this only has meaning if there is a spec, right? Someone has to write the specification, and people believe they're going to say, I want a program that does X in natural language, and they're going to get back something with a check mark. No, we have to tell people we're going to get probably back the codes and a specification of what the AI thinks you are asking, and you have to be able to read the specification and say, yes, this is what I want.
Thank you very much. Thanks a lot. We have a few other very interesting questions, but unfortunately, we will stop for a break. And we will have time during the panel discussion. I hope you will join us, Leo.
Yeah, we will.
More questions. Excellent, excellent. So we will resume in 17 minutes.
Great.
Thank you, everyone.